Thank you.
Okay,
Thanks.
thank you very much, Hans. So our next speaker is Dr. Clemens Helmbrecht, and he will present us his data on limits and highlights of detection with the ZetaView nanoparticles tracking analysis.
Very good morning. Thank you for introduction of this title. As you can see, we are from Particle Metrix, another company, and I might just a little bit highlight what we are doing, because I'm not sure if you're aware that Particle Metrix exists. And we have been long in the field, especially for zeta potential measurements and DLS systems. So basically what we do is characterization of nanoparticles in suspension, and we provide measurement techniques for both sides of the concentration range, for the higher range and for the lower range. So those instruments here are DLS and zeta potential measurements for the high concentration range. What I mean by high concentration, let's say up to 30% of weight concentration, but this also goes down to 0.001%. On the other hand, we are more known by the ZetaView instrument, and the microelectrophoresis technique actually is quite old. So back in the 1807 years, you had to use a stopwatch and a magnifying glass in order to really trace what the basis is from the electroosmotic or the electrophoresis measurement, basically how fast your particles are, so the electrophoretic mobility. Then with the computers, when they came up in the 1995, the company CAD invented the first automated tracking. So they had also an inverted microscope in order to visualize the particles and do this on an automated basis. So at this point, you really saved a lot of time. And then in 2006, Particle Metrix launched the ZetaView instrument, which does the zeta potential. And basically, so we are strong in the zeta potential field, and we found out actually with this technique, we can measure particle size as well in order to record the Brownian motion. So the key questions, basically, our companies here is from the customers. We have the questions on the right-hand side of this table. So they're asking us how much, and of course, this is the concentration, and this gives you information in the realm of nanomedicine about doses and dosage and toxicity, and of course, particle size as well tells you something about the pathway of the nanoparticles in tissue, and zeta potential as well. So zeta potential can explain something about the interaction between particles and the surfaces. So what brings me here is I focused the talk on the nanoparticle tracking analysis, where you visualize the particles via a laser. The laser shines within your dispersion, and then this light reflected from the particles is governed by an objective and magnified onto a video camera. And by taking a video, we analyze the video, and step by step we measure from the displacement of the particles, the particle size distribution. So it's not only size what we measure. By counting all the particles, we are able to measure the real concentration, the number-based concentration, and the zeta potential when we apply a voltage on the electrodes which are built in the system. So this is the principle, basically. This is a real-time video of 40 nanometers of gold. We collect an image, and by the analyzation of the video, we can really form single tracks. So this is a single particle analysis technique. We detect and localize the particles, and by mathematics, we can really calculate the particle size distribution from the mean square displacement. This is basically the jumps the particles do from frame to frame. And with the Stone-Einstein equation, we are able to get the particle size of a single particle. And if we do this for many, many particles, we get a particle size distribution. So this is an example for parenteral nutrition. You see the two curves are, for example, in range. And then if you exceed a certain diameter, you exceed the stability criteria. So the particle size here is a criteria for a quality of your product. So get a fast result, you visualize your particles, and you get an idea about the concentration. We also conducted a study, a clinical study for more than 150 patient samples. This was done with isolated EV samples, and it is able to do up to 120 measurements a day with our system. But I think I'm not telling you a secret. 150 measurements doesn't mean 150 samples. So you always should take care to do a reproducible measurements, so at least a threefold, a triplicate. And so in technical environment, we are able to do 40 to 50 full characterizations of a sample. That means concentration, zeta potential, and particle size distribution. This is an example of a yield of a quantification of an EV isolation kit. A lot of people want to save time in order to use, mostly you have an ultracentrifuge in order to isolate the particles, and the kits are available in order to separate exosomes from the rest of the sample. And with our system, we were able to do kits comparisons. You can really see, based on the concentration and the particle size distributions, that those kits are different. And by the visualization, most of the time you can tell if those kits are really working or if they do something else. Talk about reproducibility. This is the real data of a polystyrene sample, and we did a 3-day measurement, an intraday comparison, and our system is better than 5% in variation from day to day. Also, we are able to label. Whenever you label your particle with a fluorophore, we also see the fluorescence. We can trace fluorescent particles, and this gives you really a strong tool for a chemical characterization, a biochemical characterization. And we excite the particles, and you see the fluorescent light, and of course the laser light is blocked, so only the fluorescent light can go to the camera, and with the filter on and off in place, we can measure ratios of fluorescence. We can simply detect those particles and give particle size distribution. So zeta potential as well is a very nice tool because it gives you information about stability, particle charge, surface interactions. So the zeta potential is calculated by the electrophoretic mobility when you do apply a field, and in this time-lapse movie we apply the field in alternating directions. So of course, having such a strong tool, you can really study agglomeration. For example, this is done for gold. Everybody knows as soon as you add some salt, you can really see agglomeration, and this agglomeration manifests in a change in particle size distribution as well in a shift in the zeta potential distribution. And the same thing was done with the extracellular vesicles. So whenever you change the salt concentration, you see a shift in particle size distribution as well in the zeta potential distribution. And the change in particle size distribution can be explained by the shift in zeta potential. That means so the electrostatic shielding is not as strong, and the vesicles start to interact with each other. So what happens if you have mixtures? So here you see a mixture of 60 nanometer gold and polystyrene. Of course, if you mix them together, you see a nice particle size distribution showing 60 nanometers, but you do not know, does it belong to the one or to the others? So when you really look at the movie, you see that particles are much stronger in intensity, and then there are particles which are not so strong in intensity. They are scattering rather weakly. And this behavior you only see if you really look at it with a microscopic technique. And by applying algorithms, we can really separate from each other when you take into account the intensity of the particles. So we have here a scatter plot where we scale the particle size on the x-axis, on the y-axis the intensity of the particles, giving two distributions. You can plot, can come up with a heat map, and this heat map is really an identification, a fingerprint, if you want, from your particle, from your inhomogeneous particle dispersion. And by calculation, you can really trace back which belongs to which, and so you have separate particle size distributions from these subpopulations. So what we can do is, with the instrument, we can do size, we can do count, the concentration, the zeta potential distribution. Then if you apply fluorescence, we just label it FNTA for fluorescent NTA, and TNTA for the image features, where you can really, by the basis of the analysis of the image, you can trace your differences of the subpopulations. Having said this, NTA is not only in the nanomedicine field a very powerful tool. It also works for all kinds of bio-nanoparticles, polymers, nanometals, nanobubbles. This is an emerging field in Asia. And we are able to measure even in distilled water with no salt background at all. So having said this, I want to say thank you for our cooperation partners and thank you for your attention.
Thank you very much, Clemens. So any questions from the audience? Please, can you just use the microphone there? Would be nice, thank you.
Hiya, Clemens. So, I mean, I was just wondering, I saw the slide on fluorescence, and I noticed in the video clip there was Brownian motion, of course.
Yes.
But there was, it was static except for Brownian motion. So I'm just wondering, how do you deal with the fact that, of course, the fluorophores, when they are illuminated by laser, they will photo-bleach very quickly. In other words, I don't know, perhaps, well, that's a question, essentially. Yeah.
In every case, thank you for this question. You're right. Photo bleaching is crucial if you have a fluorophore and something which is absorbing light. Photo bleaching, of course, if the intensity is too high or the time is too long. In this case, both is reduced to a level that photo bleaching, with this sample, it did not occur, but I'm very aware that there are very fragile samples you have to take care, and there are different ways to do that. We can induce a flow, so we can measure different subsamples. So we are able to measure different subsamples with our instrument up to 11 positions, and we also have a pump, so we can push the particles an increment forward. An increment, this is in the range of 5 to 10 microliters, and by that we avoid photo bleaching. Thank you for this question.
Okay, thank you.
Any further question? You mentioned as one of the applications toxicology, as I'm personally come more of the biosafety area. So which applications you use it for, let's say, in the field of toxicology?
Yeah, basically NTA is a technique where you can go down to very low concentration level. So down to 10 to the power of 4 particles per milliliter. This is a very low number, and basically on the concentration and particle size. But again, I want to point out this is a physical characterization. We cannot tell if this is potentially toxic or not. So we don't know if, okay, based on some physical parameters, we could guess, to be very honest, if it's a silicon dioxide or gold. We could see that by the refractive index. But again, this is not a truly chemistry technique, and by that you really need to address other instrumentation techniques in the biotech field in order to assess, for example, by cell death, or also if those particles are potentially harmful or not.
So you would call it more, it could help in certain cases because it's so sensitive.
Yeah, it's a good, for concentration and particle size, it's very sensitive. It goes down, as I said, to the 10 to the power 4 level, which is quite low.
Okay, thank you very much, Clemens. So